Welcome back to this next video in which we are discussing fraction fields. Okay, so what we now want to do is define a multiplication law on our fraction field. Okay, so let's go for it. So let's say we've got some equivalence class here, so we'll have a over b bar, the equivalence class that contains the fraction a over b, and we want to multiply it with another equivalence class here, c over d bar, the equivalence class that contains the fraction c over d. And this is the multiplication that we're attempting to define here, so I'll colour it in red. This is going to be multiplication in our fraction field. Okay, so how are we going to define this? Well, what we're going to do is similar to in the case of addition, we're going to pick a representative from both of these equivalence classes, and we might as well pick the representative a over b from this one and the representative c over d from this one, but one of the first things we'll prove is that it really does not matter which representative you choose. Okay, and what we're going to do is use those two representative fractions to construct a third fraction, and the way we're going to do it is we're going to multiply the two numerators together in the integral domain, so we'll do a times c, we'll multiply the two denominators together, so we'll do b times d in the integral domain, we'll construct this new fraction a times c over b times d, and then we'll take the equivalence class that contains that new fraction, and that will be our answer to what the equivalence class a over b bar times the equivalence class c over d bar is going to actually be equal to in our field of fractions. And I'll stress that this multiplication is in the original integral domain. Okay, now we will always end up with a new fraction here, okay, because when we multiply a and c together we'll end up with some other element of the integral domain capital D, and when we multiply b and d together again we'll end up with some element of the integral domain that isn't the additive identity, okay, and that will be because b and d were not equal to the additive identity because they were denominators, and when you multiply two non-additive identity elements together in an integral domain you end up with an answer that is not the additive identity. Okay, so this will be a fraction that we end up with here, and then we'll just take the equivalence class that contains that fraction. Okay, so this is how we're going to define multiplication in the field of fractions. And the first thing we want to make sure of is that this is a well-defined way to multiply equivalence classes of fractions. So what we want to make sure of is that if we take another representative of this equivalence class, let's say a prime over b prime, okay, so this is related to a over b here, so I'll just put that in. Okay, so I've got another representative here, and I take another representative of this, whoops, okay, another representative of this equivalence class here, so I'll have something that's related to c over d here, so I'll have c prime and d prime. Okay, so I've got two new representatives of these equivalence classes, and now what I'm going to do is use these two different representatives to construct another fraction. Okay, so I'll multiply their numerators together, so I'll do a prime times c prime, and multiply their denominators together, so I'll do b prime times d prime, and then what I want to show is that this will be in the same equivalence class as a times c over b times d. Okay, so I want to show that this will be related to a times c over b times d, and if that's the case then of course this will be well defined, because even though we end up with a different fraction here it'll be in the same equivalence class, so the answer in terms of equivalence class, which is all we care about after all at the end, will be the same. Okay, and therefore it will be well defined. If I hand the problem of multiplying two equivalence classes to two different people, we'll get the same answer back again. Okay, right, so I'm given these two and I want to prove this, so I'll put a little question mark above that because that's what we want to prove. Okay, so remember, if these two things are true, then we can get certain statements about these numerators and denominators. We know that a times b prime, the numerator here times the denominator here, will be b times a prime, the denominator here times the numerator here, and equivalently over here we know that c times d prime will equal d times c prime. Okay, so those are the two statements that we know are true about these numbers in the integral domain. Okay, and what do we want to prove? In order to prove this, we need to prove that the numerator here, which is a prime times c prime, times the denominator here, which is b times d, is equal to, and I'll put a question mark in front of that, well above that, b prime times d prime, the denominator here, times the numerator here, which is a times c. So we need to prove that this is true. Now why is this going to be true given that these two things are true? Well, look at this. Here we've got a prime times b. So we're using the fact that multiplication obeys associativity and commutativity in our integral domain. Okay, so it doesn't matter what order we have them multiplied in. So we've got a prime times b there. Okay, so that's exactly this thing here. Okay, and on the other side, we've got b prime times a, which is exactly this thing here. Okay, then also on the left hand side here, we've got c prime times d, which is exactly this thing here. And then on the other side, we have d prime times c, which is exactly this thing here. Okay, so what you can effectively do is just substitute in for a prime times b here, a times b prime, and you can substitute in for c prime times d here, c times d prime, and that will turn this into this. So indeed, these two things are exactly equal to one another, given that these statements are true, and therefore these two fractions are related to one another if these two relations are true here. Okay, so multiplication is well defined then. If you pick different representatives of the equivalence classes of fractions that you wish to multiply, you'll get the same answer. It really does not matter. Okay, so that's good. Now let's make sure that this definition of multiplication, along with the definition of addition that we've already got on this field of fractions, is actually going to satisfy the remaining axioms of a field. So there's 6 more axioms to make sure of. Okay, so the first one is that multiplication needs to be closed. Okay, so pick any two equivalence classes of fractions. So let's say we've got a over b bar, and we've also got c over d bar here, which are elements of our field of fractions. What we need to prove is that if we multiply these two equivalence classes together, a over b bar times c over d bar, that whatever we get is still an element of the field of fractions. Okay, so the answer is always going to be another equivalence class of fractions. Okay, well again, this is very, very simple to do. So when we do this, when we multiply a over b bar with c over d bar, we create this new fraction, and this is going to be a fraction because a times c will be an element of the domain and b times d will be an element of the domain except the element 0, so you'll never get the additive identity on the bottom. So you will get a fraction here, as we've already discussed, and then all fractions are in an equivalence class, so you will always get an equivalence class back again. So the answer will always be an equivalence class of fractions. How can you possibly not end up with an equivalence class of fractions? Okay, so the way that we've defined this means that this will always spit us out another element of the fraction field back again. Okay, so that's fine. Okay, so closure's fine. Axiom number 2 is multiplicative associativity. Okay, so what we want to prove is that if you take 3 equivalence classes of fractions, so for all a over b bar, c over d bar, and e over f bar, okay, that you can possibly pick from your field of fractions, we want to prove that if you multiply these 3 equivalence classes of fractions together, it doesn't matter where you put the brackets. So we want to prove that a over b bar plus, or rather not plus, multiplied by c over d bar multiplied by e over f bar, and let's put the brackets firstly around these ones here, is equal to a over b bar times, and then we'll have the brackets in the other position, so we'll have c over d bar times e over f bar. So again, this is not difficult, we just need to work out both sides and show that they are absolutely equal to one another. Okay, so all of these multiplies here, they are in the fraction field now. Okay, so let's start off with the left-hand side. So doing the left-hand side here, so we need to take a representative from here, a representative from here. Let's pick sensible representatives, so we'll just have a over b from here and c over d from here. We construct the new fraction, which is a times c over b times d, and then take the equivalence class that contains that fraction. Then we want to multiply that by e over f bar here. Okay, again what we're going to have to do is just take a representative from here, take a representative from here. We'd be mad not to use this representative again. Okay, so this is an element of this equivalence class of fractions, so why not use that? So again we'll use this, and we'll construct a new fraction from this representative and this representative here, so we'll get ac times e over bd times f, and again we know that multiplication in an integral domain obeys associativity, so I won't bother putting brackets around the multiplication here, which is in the integral domain, so we don't need to worry about that. And then we're just taking the equivalence class that contains that overall fraction that we've constructed here. Okay, so here's the answer to the left-hand side, and in fact actually I will put brackets in here just to stress a point. So strictly speaking, we should have brackets in here. I know I just said I wasn't going to do that, but actually it will help us. Otherwise, when I do get down here, there will be absolutely nothing different between the two. But if we put the brackets in, you will see the slight difference. Okay, so I'll put the brackets in like that, because firstly we multiplied a and c together and b and d together, and then we took the answers and multiplied those by e in the integral domain and f respectively. Okay, so now let's do this side here. So we'll do this one here, so we'll take a representative from here, a representative from here, multiply the numerators together and multiply the denominators together to construct this new fraction, and then take the equivalence class that contains that. Then we'll want to multiply this equivalence class of fractions with this equivalence class of fractions. Okay, so here is still multiply in red there. Okay, so we'll take a representative from here, a representative from here. Again, we'll pick sensible representatives and we'll construct a new fraction from them. So we'll get a times c times e, and then the denominator will be b times d times f, like so. And then we'll take the equivalence class that contains that. Okay, so this will be the answer to the right-hand side here. Okay, so now because of multiplicative associativity in the integral domain, it really does not matter that you've got the brackets around a times c here and the brackets around c times e here, and the same for the denominators. The numerator is exactly equal to this numerator, the denominator is exactly equal to this denominator, so you are taking the equivalence class that contains the exact same fraction, so these two equivalence classes are equal to one another. So indeed, multiplicative associativity does hold true. Okay, so that's very nice. Okay, right, now let's go on to axiom number 3 that multiplication must obey. This is the existence of a multiplicative identity. Okay, so what I want to show you is what element is going to be our multiplicative identity. Okay, so it's going to be the equivalence class that contains the fraction 1 over 1, which is a fairly intuitive thing for the multiplicative identity to be. Now, what other fractions are going to be in this equivalence class with the fraction 1 over 1? Okay, so let's ask which other fractions, a over b, will be related to 1 over 1? Well, if this was true, it would be true that 1 times b was equal to 1 times a. So it's all fractions of the form a over a, so where the numerator and the denominator are equal to one another. So this equivalence class looks like this. All things of the form a over a, where a is an element of the domain, but I should stress, of course, that a is not allowed to equal 0, so I should put except 0, because you can't have 0 in the denominator, so 0 divided by 0, or 0 over 0 rather, you're not allowed to have that one. Okay, but all the other fractions, they are going to be in this equivalence class with 1 over 1. Okay, right, so let me just prove then that this equivalence class of fractions is indeed our multiplicative identity. Okay, so what I want to prove then is that if I take this equivalence class of fractions, the equivalence class containing this fraction 1 over 1, and multiply it by any other fraction, or equivalence class of fractions, okay, so the equivalence class containing a over b here, okay, so this is multiplication in my fraction field. What I want to show is that this is going to give me the equivalence class containing a over b back again. Okay, so how am I going to do this? Well, of course, if I want to multiply these two together, I take a representative from here, take a representative from here. Why not pick the most natural representative, 1 over 1? That is the most natural representative to use. You could use others, but why bother? This is a really nice one. Okay, and then, of course, we multiply the numerators together, so I'll take the representative a over b from here, multiply the numerators together and I'll get a, multiply the denominators together and I'll get b, so I'll just take the equivalence class that contains the fraction a over b. Okay, and of course, that's equal to the original equivalence class that we had here. So, hopefully you can appreciate that if you did it the other way round, if you had the arbitrary equivalence class on the other side and the multiplicative identity on this side, that it would be the same result. This equivalence class containing the fraction 1 over 1 will multiply by any other equivalence class to give that other equivalence class back again, either way round that you do it. Okay, so it's our multiplicative identity. Okay, so there's our multiplicative identity. Right, Axiom number 4 then, so I'll go into this position here now. Axiom number 4 is that we need multiplicative inverses. Okay, so you give me any equivalence class of fractions. So if I have the equivalence class containing the fraction a over b, I need to find another equivalence class of fractions which will multiply by this to give me the multiplicative identity back again, which is this equivalence class containing 1 over 1. Okay, well I claim this is very simple. Just consider the equivalence class containing the fraction b over a. Oh, and I should stress, we need to be able to do this for all elements apart from the equivalence class which is the additive identity. Now let me just remind you of what the equivalence class which is the additive identity is equal to. That's the equivalence class containing this fraction 0 over 1. Okay, and indeed it contains all things of the form 0 over something. Okay, now if I attempted to construct this equivalence class here for this, what I would end up doing is constructing 1 over 0, the fraction 1 over 0, and that's not a fraction. Okay, so that's why you can't find a multiplicative inverse for the additive identity, and we know that that's convincing a sign that we're actually going to end up with a field here, because we shouldn't be able to find a multiplicative inverse for the additive identity. Okay, but for all other fractions where a is not going to be equal to 0, we can do this. We can swap the numerator and the denominator around, and we'll get this new fraction, and then we can ask which equivalence class contains that fraction, and we'll get some element of the fraction field. Okay, so for all elements except an additive identity, or except the additive identity equivalence class here, you can construct this other equivalence class here. Okay, now let's ask what happens if I multiply the equivalence class containing a over b by this equivalence class b over a bar here. Okay, well how would I do that? Well, I'll do it just with my definition. So my definition says take a representative from here, take a representative from here, okay, construct that new fraction and then take the equivalence class that contains that. So I'll take the representative a over b from here, and I'll take the representative b over a from here, I'll construct the new fraction and I'll get ab over ba, and I'll take the equivalence class that contains that. But of course a times b is the same as b times a, so I've got a fraction which is the same thing in the numerator as is in the denominator, and of course that is going to be in the same equivalence class as 1 over 1, so indeed this is the multiplicative identity in my field of fractions. Okay, so for any equivalence class that is not of fractions, that is not the additive identity in my fraction field, I can find you a multiplicative inverse by doing this, finding this equivalence class that contains a swapped over fraction in this way. Okay, right. Now, axiom number 5 then. Commutativity. So I want to prove that multiplication obeys commutativity. This is a nice simple one as well. So what I want to prove is that if I have one equivalence class of fractions, a over b bar, and I multiply it by another equivalence class of fractions, c over d bar here, that it's the same if I do it the other way around. So if I multiply c over d bar by a over b bar, like so. Okay, and this of course is multiplication in the fraction field. Okay, so quite simply, work out what it is for the left-hand side, work out what it's going to be for the right-hand side, and show that they are equal to one another. Okay, right. So if we're working out the left-hand side here, we'll take a representative from here, take a representative from here, and construct the new fraction. So we'll take the representative a over b from here, and the representative c over d from here. Okay, so we'll multiply a and c together. Okay, and then we'll multiply b and d together, and we'll take the equivalence class that contains that fraction. So this is the left-hand side here, and then we'll do the right-hand side. So again, we'll pick the same representatives, we'd be stupid not to. So we take the representative c over d from here, and the representative a over b from here. We'll multiply the numerators together, and put it over the two denominators multiplied together, and then take the equivalence class that contains that. And of course these two fractions are exactly equal to one another because of commutativity of multiplication in the integral domain. Therefore we're asking for the equivalence class that contains the same fraction, so these two equivalence classes are going to be equal to each other. Okay, so that's a very simple proof that multiplication would obey commutativity. Okay, so finally, the most difficult one to prove in this case. Okay, distributivity, axiom number 6, distributivity. Now, we only need to prove one of the distributive laws. We don't need to prove left and right distributivity because we've already proven commutativity. Okay, so the instant you've got left distributivity and commutativity, you also have right distributivity. Okay, so we'll just prove left distributivity. Okay, so what we want to prove is that if you have one equivalence class of fractions, a over b bar here, and you multiply it with with the sum of two other equivalence classes of fractions, so c over d bar plus e over f bar here, okay, and I'll stress that this is addition in our field of fractions and this is multiplication in our field of fractions here. I've just dropped the multiplication sign. That this is equal to, okay, here this means firstly add these two together and then multiply. It's going to be the same thing as if we firstly multiply and then add. So if we firstly multiply a over b bar with c over d bar, okay, and we multiply a over b bar with e over f bar, okay, and then add the two of them together. Okay, so this is multiplication again in our field of fractions and then addition here. And this means firstly do the multiplications and then get the two answers here and add them together. Okay, so how am I going to do this? Well, again, what I'm going to do is take the left-hand side, take the right-hand side, work them both out and show that they're equal to one another. And this actually is the least trivial of all the things that we've done. It's still not difficult, but it is the least trivial. Okay, so let's do it then. So let's start off with the left-hand side here. So, what we'll start by doing then is adding these two together. So we'll take a representative from here, take a representative from here. We'll always take sensible representatives, so we'll take the c over d and the e over f. Okay, we'll construct this new fraction, which is c times f plus d times e over d times f, and we'll then take the equivalence class that contains that. Then what we'll want to do is add on a over b bar, so we want to add this equivalence class to this equivalence class, okay, and this is addition in the field of fractions. So we take a representative from here, take a representative from here, we'll take a over b from here, and of course this thing from here. We will then, not add, almost a very terrible mistake there, multiply, that should be multiply. So we've added those two together and we've multiplied here, so this is multiplication, not addition. Okay, almost a terrible mistake. Right, so if we want to multiply a over b with this, of course that's even simpler than adding them, so I just want to multiply this numerator and this numerator, so I'll just apply distributivity of, and that shouldn't be a b, that should be an a. Terrible mistakes. Right, okay, so we'll just apply distributivity in the integral domain of multiplication over addition, so we'll get a times c times f plus a times d times e, and again I'm assuming that we understand that multiplication is associative, so I'm not bothering to put any brackets in. Okay, it just becomes a nightmare if you insist on actually doing it rigorously with all of the brackets and things for the integral domain operations. Okay, and then underneath we'll have the denominators multiplied by one another, b times d times f. So we've constructed this fraction and then we just want the equivalence class that contains it. Okay, so this is the example, this is the answer that we'll get on the left-hand side. So when we work with the left-hand side, we get this. Okay, now let's work with the right-hand side here. Okay, so we want to multiply first. So we'll multiply this one and this one together, representative from here, representative from here. Okay, multiply the numerators together and the denominators together, and then take the equivalence class that contains that. And then we want to add it to these two multiplied together. So we take a representative from here, multiply the numerators, a times e, and multiply the denominators, b times f, and then take the equivalence class that contains that fraction. And then we want to add these two equivalence classes together. Okay, so again we take a representative from here, take a representative from here, we'll take the obvious representative from here and an obvious representative from here. So now we want to add them together, so we need to take this numerator and multiply it by this denominator. So we'll get ac times b times f here, and again I'm not bothering to put in brackets for where the multiplication is in the integral domain because we know it obeys associativity anyway. Okay, and then we'll have plus this denominator here, b times d, times this numerator here, a times e, and then it will all be over b times d, this denominator here, times b times f, this denominator here, and then we'll take the equivalence class that contains that. Okay, so this is why I said this was the least trivial, okay, because now, is it instantly apparent that these two are the same equivalence classes? Well, it's not as instantly apparent as it was over here. Okay, we're going to have to do a little bit more work now. We need to prove that this fraction here is in the same equivalence class as this one. Okay, so we need to prove that this fraction is related to this one to prove that these two equivalence classes, the overall answer on the left and the answer on the right, are equal to one another. Okay, so what we need to prove then is that this numerator times this denominator is equal to this denominator times this numerator. So let's do that. Okay, so this numerator here is a times c times f here, and I'll just move this up a little bit. Okay, plus a times d times e, and this is the part where I find out whether I've made some ghastly mistake. Okay, and then we multiply it by this denominator here, b times d times b times f. Okay. And then we want to ask, is this equal to, so I'll put a question mark there, the denominator here, b times d times f, times the numerator here, which is a times c times b times f plus, and then we've got b times d times a times e. Okay, right, so now we just have to apply distributivity and pray that I haven't made a mistake and that the two things do correspond between on either sides of the equals. Okay, so applying distributivity then, the first thing we'll get here is a times c times f times all of this, b, d, b, f. Okay, and then the second thing we'll get is plus a times d times e times b times d times b times f. Okay, so that's the left hand side. Now let's do the right hand side. So we'll get b times d times f times a times c times b times f plus b times d times f times b times d times a times e. Okay, so which one is equal to which one? So let's compare these two here. So we've got an a in both of them. We've got two b's, that's good. Okay, we've got how many f's? We've got two f's, that's all looking good. We've got one c in both of them. And then which is the other element? Okay, what have I done wrong? Oh, d as well, we've got d. I'll have to colour code this to keep track. So we'll have an A here, okay, between both of them. Got a C here, there's the C. Okay, we've got two F's, so we've got those two F's there. Okay, we've got the two B's, which are there. Okay, this is looking good. And then we've got the D. Okay, so those two things do correspond. So that's now hope for the other two. Okay, so A here, we've got one A, that's over there. Okay, we've then got two D's here, so 2D is there. Okay, we've got one E in this expression here. Okay, that's over there. Then two B's, oh, I shouldn't probably use the pink, so we'll have red instead. So the B's are in red here. Got two B's there. Okay, and then finally, of course, that F, and I'm struggling to know which colour to use, orange now. We've got F in orange here. Okay, there we go. So those two do correspond as well. So this is true. It is true that this fraction is equivalent to this fraction, and therefore these two equivalence classes that we've got here are equal to one another, and therefore, yes, the left-hand side here is equal to the right-hand side here. Left distributivity does hold, and because we've got commutativity and left distributivity, right distributivity will therefore hold, and that's now all of the axioms of field theory proven to be true. Okay, so this structure that I have constructed, this set of equivalence classes of fractions with these laws of addition and multiplication that I have defined on it, is indeed a field. Fantastic. Okay, I'll stress again that you must start off with an integral domain. What we will do in the next video is we will prove that there is an injective homomorphism from our initial integral domain into this field of fractions, so that you can truly think of this field of fractions as an extension of the integral domain to make it a field.